Okay, we've got patterns with shapes. Let's go. Look at the pattern below. Now, before I say anything, before I talk about the problem itself, I want to say that this kind of problem, where there are tiles that are getting more and more or less and less, and the students have to come up with what the pattern is, that is something students will carry through with them all the way through into high school. It is a very large part of how we define things like sequences, things like linear and exponential functions. This is once again building a very solid foundation for something your students are going to be seeing over and over and over again in math. So do not skip or make light of these kinds of problems. They will be helpful later on down the line. How many squares will be in the pattern at the 8th step? Again, I am so in awe of the fact that we are seeing this problem in 4th grade, because in a high school class, this is a quadratic expansion. We would have to like throw x squareds around and stuff to figure stuff like that out. But because we're keeping the pattern fairly simple, and because we're keeping it to step 8 instead of step 80, we can probably just count out. When it comes to stuff like this, I really like just asking students in a group to sit down and just explore the pattern. What do they think is happening every time? Some students will be like, oh, well, let's see. It looks like in step 2 here, this is the original square, right? That's the original one from step 1, and it added 2 in a diagonal. Okay. And then step 3, well, here's the 3 from step 2, right? That's the shape from step 2 right in there. And it looks like it's adding 1, 2, 3 more squares in a diagonal. And hey, look, this next one over here, the shape from step 3 is right here. And it's adding, 1, 2, 3, 4. So it looks like the rule is plus 2 plus 3 plus 4, yeah? So for step 5, we're going to add another 5. For step 6, we're going to add another 6. Same for step 7. Same for step 8. And now we just have to total them all up. 2 and 3 is 5, and 4 is 9. And 5 is 14, just making sure, and 6 is 20, and 7 is 27, and 8 is 35, is what I got with my very quick mental arithmetic, which is always fallible, so be careful. But again, this is only one of many patterns that students could see. Check this one out instead. What if instead they said, okay, well, I've got 1 here, and then it adds this column of 2 here the second time. And then it adds this column of 3 here the third time. Adds this column of 4 here the fourth time. You get the same rule. But it's a totally different way of looking at it. I really strongly advise giving students access to problems like this and just letting them explore. Don't coach. Don't guide, let them find their own patterns. And the patterns they can find will become more complex as they get older and learn more about this stuff. My mental math must have been wrong because 35 isn't one of the options. I think I left out step 1. That was my problem. So I think it's 36. Yeah, I just forgot to count step 1. Easy mistake to make. So this is the same pattern. I keep gesturing at my camera as though it was on, and it's not. How does the pattern grow at each step? Well, we determined that it grows by 2 squares, then 3 squares, then 4 squares. We are adding 1 to the amount that it grows by with every iteration, and that, believe it or not, is what defines a quadratic formula later on down the line. In the following pattern, every group of rectangles has 1 more rectangle than the group before it, and there is a rhombus before every group. I like that we're throwing these words like rectangle and rhombus around. That's not what I meant to do. there we go. Like rectangle. I know adults that don't remember what a rhombus is, and I know high school students who were taught it last week who don't know what it is. A rhombus is any four-sided figure that has all four sides the same length. A square is a type of rhombus, but you can also sort of flatten it out so long as the four sides are all the same. Okay, every rhombus is an odd-numbered shape. Well, that's not right because it's 6, or because this rhombus is 6. The next group will have 4 rectangles. Well, that's true because the rule is every group of rectangles has one more rectangle than the group before it. We had a group of 1, a group of 2, a group of 3. The next group will have 4. Now, is shape 15 going to be a rectangle? Well, we know the next 4, 11, 12, 13, and 14. 11, 12, 13, and 14 are all rectangles. 15, however, will be a rhombus. Psychanthrope says, I'm one of the adults who don't remember what a rhombus is. I would have called those diamonds. Yes, and most students want to call them diamonds as well. The problem is, or diamond is a wonderfully descriptive word in the English language that gives you an immediate idea of what the thing looks like. It's not a mathematical definition, right? A mathematical definition has to be things, you know, has to be a little bit more precise. But yes, calling it a diamond is something that I encourage my students to do at first. I say, yes, it is a diamond. What else is it? And that really gets students thinking about how one thing can have multiple names. This thing right here, despite my crappy drawing, is a square, but it's also a rectangle. It's also a quadrilateral. It's also a rhombus. It meets the criteria of all those things. And making that distinction is a big step for a lot of students and adults. Allie the turtle was born with 1 square on her shell. When she was 1 year old, 8 new squares appeared around the old squares. Each year, a new group of squares appeared around the old squares. Again, we're talking about a quadratic expansion here, but... Okay, so at age 2, how many more new squares will there be? And again, oh, I love problems like this so much. Okay, so here's step 1, and here's step 2, yeah? And again, I would ask students maybe to draw age 2, and they would probably draw something like, well, okay, got black square, and then you've got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8 around there. And then I guess we'll make them red. 1, 2, 3, 4, 5, 6, 7. You see the problem here? It'll work. But do we really want to count all of these? I like problems like this because it makes it clear that the mathematical problems are not the thing causing the issue. It's the solution to the problem. I don't want to have to draw another layer of those and then count them. Okay? I would much rather find some kind of shortcut, and math is all about shortcuts. So what I would do is I would go ahead and have the students write or draw the third image here at age 2, and then I would ask them, okay, now what do you notice about how this is expanding? And there are lots and lots of potential answers. I'm going to give mine, but mine is by no means definitive. It looks to me that when we make the next larger square, each side is duplicated, yeah? This 3 became another 3. This 3 became another 3. So each side is duplicated, but then we're also adding in these 4 corner pieces. So in order to get the next bigger one, we're going to have to add, again, each of these sides we're going to expand out, and then we're going to add 4 corner pieces. I hope that makes sense. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20, 25. We're at 25 right now, so I'll go ahead and put that in here. But now, to add it again, instead, I'm just going to go ahead and say, all right, well, the next one's going to have, I'm just going to count up all of the, I'm just going to count up all of the squares here, the red squares specifically. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I see 16 of these red squares. So when we expand out to the next one, we're going to add another 16. And then we're going to add 4 more for the corners. So we're actually adding 20. 25 plus 20 is 45. Again, this is a 38-year-old math teacher's way of seeing this problem. This problem is not intended to be solved in one specific way. It is intended to serve as an exploration ground for students so that they can see how numbers and shapes are related. If you teach something like this, I recommend... Oh no, what did I do wrong? I miscounted. Oh, because it's the number of new squares, not the number of total squares. Ha, see? Reading comprehension, friends. I wish I had a camera on so I could cut to it and look at it like, oh my god, I can't believe I made that mistake. It happens, though. So, I misread this. I said total squares. But that's not what it wanted. It wanted new squares. So, wording is very important. It's very easy to get tripped up in the words, and there is nothing wrong or shameful about that. As a math educator, it is my job to see if I can pick out where the misunderstanding is so that I can address it, rather than passing judgment on my students for not getting the right answer somehow perfectly the first time, when I don't always get the right answer somehow perfectly the first time. I honestly love making mistakes in front of my students because it shows them that mistakes are okay. 16, 24.